Conduct electricity. Part 1. A substance that allows electric current to pass through it must contain mobile charged particles. These particles, which can be either electrons or ions, are called charge carriers. The charge carriers carry charge across the substance, and we say that the substance conducts electricity. On the basis of the nature of the charge carriers, conducting substances are classified into electronic or metallic conductors and electrolytic conductors. Electronic or metallic conductors. Substances which conduct electricity due to the presence of mobile electrons are called electronic or metallic conductors. Metals, alloys, and the non-metal graphite are electronic conductors. They have comparatively loose, that is, mobile electrons which carry charge across them. They conduct in the solid as well as in the molten state, and no chemical change occurs when an electric current passes through them. Let us now learn about electrolytes. There are many substances, that is, NaCl and KOH, which do not have mobile electrons, and yet conduct electricity in the molten state or in an aqueous solution. Under these conditions, they form mobile ions which carry charge across them. Such substances which allow the passage of electric current through them in the molten state or in solution due to the presence of ions are called electrolytes. And the conduction of electricity by ions is known as electrolytic conduction. Acids, bases, and salts are common examples of electrolytes. Acids, that is HCl, HNO3, and H2SO4, furnish H3O+, and the corresponding anions in aqueous solutions. Bases, example, NaOH and KOH. And salts, example, NaCl and K2SO4, dissociate into cations and anions in the molten state as well as in solution. This is an extension of the Arrhenius theory of electrolytic dissociation proposed in 1887. Arrhenius thought that an electrolyte solution is at least partly broken up into ions. Depending on the extent of dissociation, electrolytes are classified as strong and weak. Conduct electricity. Part 2. Strong electrolytes. Electrolytes which dissociate completely or almost completely into ions in solution are called strong electrolytes. Due to complete dissociation, strong electrolytes exist only as ions, not as molecules in solution. Many strong electrolytes dissociate completely in the molten state also, whereas others do so only in solution. The following types of compounds are strong electrolytes. Ionic compounds. Ionic compounds, example salts, and soluble hydroxides of metals, that is strong bases, are strong electrolytes. Some examples are given below. 1. Salts like NaCl, KCl, MgCl2, CaCl2, PbBr2, NH4Cl, and CuSO4. 2. Soluble hydroxides of metals, that is, strong bases such as NaOH, KOH, and BaOH2. Another example of strong electrolytes are strong acids. Strong acids like HCl, HNO3, H2SO4, HClO4, HBr, and HI are strong electrolytes as they dissociate completely in aqueous solutions. Weak electrolytes. Electrolytes which dissociate into ions in solution only to a small extent are called weak electrolytes. Due to partial dissociation, weak electrolytes exist both as ions and molecules in solution. The following types of compounds are weak electrolytes. 1. Weak inorganic acids like H2CO3, H2SO3, and H3PO4. 2. Organic acids like CH3COOH or acetic acid and HCOOH or formic acid. 3. Weak bases like NH3 and its derivatives. Non-electrolytes. Substances which do not dissociate into ions in the molten state or in solution are called non-electrolytes. In other words, non-electrolytes remain as molecules in the liquid state, melted, or solution, and do not conduct electricity. Common examples of non-electrolytes are covalent compounds like pure water, pure acids, not in solution, ethanol, benzene, carbon tetrachloride, sugar, and paraffin wax. Conduction of electricity through electrolytes. The following experiments show that a chemical change takes place when an electric current passes through an electrolyte. Let us look at different scenarios. Case 1. If you melt some solid lead-2 bromide in a porcelain crucible and pass electric current through the molten salt, you will find that a silver-gray material collects around the cathode and red-brown vapors evolve at the anode. We can conclude that lead-2 bromide decomposes into lead, the silver-gray material collecting at the cathode, and bromine, the red-brown vapors evolving at the anode. Case 2. If you pass electric current through an aqueous solution of NaCl mixed with litmus solution and place in a U-tube, you will find that the solution in the cathode wing turns blue and that in the anode wing is bleached. We can conclude that a base, NaOH, might have been produced at the cathode, since the litmus turns blue, and a bleaching agent, Cl2, at the anode. In case of an acidified or acidulated water, you have already learned in the previous class that water decomposes into hydrogen and oxygen when an electric current is passed through acidulated water. Now, the question arises, what kind of a chemical change takes place during electrolysis? We will soon learn that the chemical change that takes place on the passage of electric current through electrolyte involves a transfer of electrons from one species to another. According to the modern view, transfer of electrons leads to oxidation-reduction reactions. That oxidation and reduction involve the loss or gain of hydrogen or oxygen is an older view. So let us study the modern view of such reactions in order to understand what happens when a current is passed through an electrolyte. Part 1. In this module, let us focus on electrolysis. The decomposition of a compound in the molten state or in solution when electric current is passed through it is known as electrolysis. Let us now learn about a few terms associated with electrolysis. The process of electrolysis takes place in a vessel called the electrolytic cell or voltameter. It contains electrodes, which are the terminals, usually metal or graphite rods, through which electric current enters and leaves the electrolyte, are called electrodes. The electrode connected to the negative terminal of the battery is called the cathode, and the one connected to the positive terminal, the anode. While choosing the electrode material, one should ensure that it does not react either with the electrolyte or with the product liberated at the electrode. A very important constituent of electrolysis is the electrolyte. An electrolyte may be a melt or an aqueous solution. Often, in the case of a solution, the solute being decomposed is called the electrolyte. For example, if an aqueous solution of CuSO4 is placed in the voltameter, the CuSO4 is said to be the electrolyte. Let us now understand the chemical reaction taking place in electrolysis. In the molten state, or in solution, an electrolyte dissociates into cations, positive ions, and anions, or negative ions. The reaction being Mn plus An minus in equilibrium with Mn plus An minus. Here, M is a metal and A is a non-metal or a negative radical like hydroxyl or sulfate. In ionic solids like NaCl or PbBr2, the ions are fixed in their lattice positions and are not free to move. But in the liquid state or in solution, the ions are mobile. Part 2. Discharge of ions at the electrodes. Being positively charged, the cations migrate, that is, move, in an electric field towards the negative electrode, that is, the cathode. And the anions, being negatively charged, migrate towards the positive electrode, that is, the anode. The cations take up electrons from the cathode and are discharged, that is, lose their charge there. The anions, in contrast, give up electrons to the anode and are discharged there. The reaction being, at cathode, Mn plus Ne gives M, 2H3O plus 2E gives H2. As electrons are taken up by the cations at the cathode, the reaction occurring at this electrode is called cathodic reduction. At anode, An- gives A plus Ne. Since electrons are given up by the anion at the anode, this reaction is called anodic oxidation. It is very important to note that the number of electrons taken up at the cathode must be equal to that given up at the anode. Metal atoms are deposited at the cathode, but H atoms, if deposited, combine to form H2 molecules. Similarly, gaseous elements like O, Cl, and Br are deposited at the anode as the molecules of O2, Cl2, and Br2 respectively. We will soon learn how negative radicals like OH- and SO2-4 behave. In case of molten solution of sodium chloride, 2NaCl gives 2Na plus 2Cl minus. The reactions which take place in electrolysis are: reaction at cathode, 2Na plus 2E gives 2Na. Reaction at anode, 2Cl minus gives 2Cl plus 2E. Electrolysis Part 3. Let us now learn about the selective discharge of ions. Suppose we choose a molten mixture of NaF and MgCl2 for electrolysis. The Na plus and Mg2 plus ions will migrate to the cathode, but only the Mg2 plus ions will be discharged there. At the same time, the F- and Cl- ions will migrate to the anode, but only the Cl- ions will be discharged there. The discharge of an ion in preference to another at an electrode is called selective discharge. The selective discharge of ions takes place because the tendency of elements to form ions differ from each other. Obviously, an element having a smaller tendency to form ions will be deposited at an electrode in preference to the one having a greater tendency to form ions. Let us see how this principle helps us understand the selective discharge of cations and anions from a mixture of electrolytes. Cations. The activity series represents, in general, the order of the tendency of metals and hydrogen to form cations. So, the cation of a less active metal is discharged at the cathode in preference to that of a more active metal. Thus, Mg being lower than Na in the activity series, Mg2 plus ions will be discharged at the cathode in preference to Na plus ions from a mixture of the two. Similarly, Fe2 plus ions will be discharged in preference to Mg2 plus ions and Cu2 plus ions in preference to Fe2 plus or H plus ions at the cathode. Exception. Though Ca is below Na in the activity series, Na plus ions are discharged in preference to Ca2 plus ions at the cathode. For example, the electrolysis of a molten mixture of CaCl2 and NaCl will yield Na at the cathode. With the positions of Na and Ca inverted, the activity series gives the correct order of the tendencies of metals and H to form and remain as ions. The character of an element to form and remain as ions is called its electrochemical character. And the order of the tendencies of elements to do so is known as the electrochemical series. This series for cations is often called the electropositive series, and that for anions, the electronegative series. Anions. Anions are also arranged in the order of the case of being discharged. The order is often called the electronegative series. We can easily understand now why Cl- ions are discharged in preference to F- ions at the anode. When a molten mixture of NaF and MgCl2 is electrolyzed. Part 4. Discharge of ions from aqueous solutions. The products of the electrolysis of an aqueous solution of a salt may be different from those obtained if the electrolyte is molten. This is because of the simultaneous dissociation of water, though to a very small extent, into H3O+, H+ for simplicity, and OH-. So in the electrolytic cell, the H+ ion migrates towards the cathode and the OH- ions towards the anode. Thus, there is more than one ion competing for discharge at each electrode. 1. The metal ion, Na, and the H+ ion at the cathode. And 2. The anion of the salt and the OH- ion at the anode. One ion will be discharged in preference to the other at each electrode as follows. At cathode, if the metal M is more active than H, it will remain in ionic form in the solution and H+ will be discharged. 2H+ plus 2E gives 2H gives H2, or 2H3O plus 2E gives H2 plus 2H2O. H3O plus or H plus ions will be discharged in preference to K plus, Ca2 plus, Na plus, Mg2 plus, Al3 plus, and Zn2 plus ions. On the other hand, if M is less active than H, Mn plus ions will be discharged in preference to H plus ions, that is, H3O plus ions. Mn plus Ne gives M. So, the ions Cu2 plus and Ag plus will be discharged in preference to H3O plus ions at the cathode. At anode, 1 Cl minus, Br minus, and I minus are discharged in preference to OH minus, and the products are Cl2, Br2, and I2 respectively. 2. OH minus ions are discharged in preference to SO4 2 minus and NO3 minus ions, and the product is O2. Copper, electrorefining. Copper of purity 98 to 99% obtained by conventional methods is further purified to 99.98% by the electrolytic method. Thick rectangular blocks of impure copper are taken as anodes, and thin plates of copper as cathodes. The cathodes and anodes are alternately hung in an electrolytic bath containing CuSO4 solution acidified with H2SO4. On passing the current, CuSO4 undergoes electrolysis. Pure copper deposits at the cathodes and dissolves out of the anodes to replenish the concentration of the Cu2 plus ions in the electrolyte. The reaction being CuSO4 gives Cu2 plus SO4 2 minus. Cu2 plus 2E gives Cu at the cathodes. Cu gives Cu2 plus 2E at the anodes. In effect, copper dissolves out of anode blocks of impure copper and deposits in the purest form at the cathodes. Some impurities like Fe, Zn, and Ni, which are more electropositive, that is, more active than copper, pass into solution as sulfates. And others like Ag, Au, and possibly Pt, which are less electropositive than Cu, settle as a mud called anode mud or anode sludge. The anode sludge is processed for the separation of precious metals. The purification of a metal by the electrolytic process, also called electrorefining, is used for several metals like Cr, Ni, Cu, Ag, Au, and Pt. Reactions in terms of electron transfer reactions. Students, we have already learned about redox reactions. Let us look at these equations. These are redox reactions because in each of these reactions, sodium is oxidized due to the addition of either sulfur or more electronegative element to sodium. Simultaneously, chlorine, oxygen, and sulfur are reduced because to each of these, the electropositive element sodium has been added to form sodium chloride, sodium oxide, and sodium sulfide, respectively. So in these reactions, both the processes of oxidation and reduction are taking place. Hence they are called redox reactions. From our knowledge of chemical bonding, we know that sodium chloride, sodium oxide, and sodium sulfide are ionic compounds. So they can be better written in ionic forms. Sodium chloride can be written as Na plus Cl minus. Sodium oxide can be written as Na plus 2 O2 minus. And sodium sulfide can be written as Na plus 2 S2 minus. The development of charges on the species produced suggests to us to rewrite the reactions in the following manner as shown here. These processes can be considered as two separate steps, one involving the loss of electrons and the other the gain of electrons. As an illustration, let us elaborate the formation of sodium chloride. Sodium loses electrons to form sodium ion. The reactions that involve loss of electrons are called oxidation reactions. Chlorine gains electrons to form chlorine ions. Similarly, the reactions that involve gain of electrons are called reduction reactions. These steps are called half reaction, which explicitly show involvement of electrons. Sum of half reactions gives the overall reaction as follows. In these reactions, sodium, which is oxidized, acts as a reducing agent because it donates electrons to each of the elements interacting with it, and thus helps in reducing them. Chlorine, oxygen, and sulfur are reduced and act as oxidizing agents because these accept electrons from sodium. Now children, let us summarize what we have learned. Oxidation is a process of loss of electrons by any species. Reduction is a process of gain of electrons by any species. Oxidizing agent is the acceptor of electrons. Reducing agent is the donor of electrons. Part 1. Students, we have learned about redox reactions in terms of electron transfer reactions. Now we will learn more about competitive electron transfer reactions. Let us perform an experiment. First, place a strip of metallic zinc in an aqueous solution of copper nitrate for about 1 hour. After an hour, we may notice that the strip becomes coated with reddish metallic copper and the blue color of the solution disappears. This is because of the formation of Zn2+ ions. Formation of Zn2+ ions among the products can easily be judged when the blue color of the solution due to the disappearance of Cu2+ ions. If hydrogen sulfide gas is passed through the colorless solution containing Zn2+ ions, the appearance of white zinc sulfide, ZnS, can be seen on making the solution alkyne with ammonia. The reaction between metallic zinc and the aqueous solution of copper nitrate can be written as Zn solid plus Cu2+ ions aqueous gives Zn2+ aqueous plus Cu solid. In this reaction, zinc has lost electrons to form Zn2+ ions, and therefore zinc is oxidized. We know that if zinc is oxidized, releasing electrons, something must be reduced, accepting the electrons lost by zinc. We find that copper ion is reduced by gaining electrons from zinc. So this reaction can be rewritten as shown. Let us now investigate the state of equilibrium for this reaction. For this purpose, let us place a strip of metallic copper in a zinc sulfate solution. No visible reaction is noticed. Also, an attempt to detect the presence of Cu2 plus ions by passing H2S gas through the solution to produce the black color of cupric sulfide, CuS, does not succeed. Cupric sulfide has such a low solubility that this is an extremely sensitive test. Yet, the amount of Cu2 plus ions formed cannot be detected. We thus conclude that the state of equilibrium for this reaction greatly favors the products over the reactants. Transfer reactions, Part 2. Let us now extend the electron transfer reaction to copper metal and silver nitrate solution in water. Dip a copper rod in silver nitrate solution. You will notice that the blue color starts developing. The solution develops blue color due to the formation of Cu2 plus ions on account of the reaction. Cu solid is oxidized to Cu2 plus ions, aqueous. Intensity of blue color increases and silver deposits on the rod. This is because Ag plus ion, aqueous, is reduced to Ag, solid. Thus we conclude equilibrium greatly favors the products Cu2 plus ions, aqueous, and Ag, solid. Now students, let us also understand the reaction of metallic cobalt placed in nickel sulfate solution. At equilibrium, chemical tests reveal that Ni2 plus ions, aqueous, are present at moderate concentrations. In this case, neither the reactants, COS, and Ni2 plus ions, aqueous, nor the products, CO2 plus ions, aqueous, and Ni, solid, are greatly favored. After studying the reactions, we can conclude that zinc releases electrons to copper and copper releases electrons to silver. And therefore, the electron releasing tendency of the metals is in the order zinc greater than copper greater than silver. Students, this competition for electrons between various metals helps us to design a class of cells named as galvanic cells, in which the chemical reactions become the source of electrical energy. Electroplating. Recall that a brand new bicycle has a shiny handlebar and wheel rims. However, if these are accidentally scratched, the shiny coating comes off, revealing a not so shiny surface beneath. You might have also seen women using ornaments which appear to be made of gold. However, with repeated use, the gold coating wears off, revealing silver or some other metal beneath. In both these cases, a metal has a coating of another metal. Do you wonder how a layer of one metal can be deposited on top of another? Well, let us try doing it ourselves. When electric current is passed through the copper sulfate solution, copper sulfate dissociates into copper and sulfate. The free copper gets drawn to the electrode connected to the negative terminal of the battery and gets deposited on it. But what about the loss of copper from the solution? From the other electrode, a copper plate, an equal amount of copper gets dissolved in the solution. Thus, the loss of copper from the solution is restored and the process keeps going. This means that copper gets transferred from one electrode to the other. The process of depositing a layer of any desired metal on another material by means of electricity is called electroplating. It is one of the most common applications of chemical effects of electric current. Electroplating is a very useful process. It is widely used in industry for coating metal objects with a thin layer of a different metal. The layer of metal deposited has some desired property which the metal of the object lacks. For example, chromium plating is done on many objects such as car parts, bath taps, kitchen gas burners, bicycle handlebars, wheel rims, and many others. Chromium has a shiny appearance. It does not corrode. It resists scratches. However, chromium is expensive and it may not be economical to make the whole object out of chromium. So, the object is made from a cheaper metal and only a coating of chromium is deposited over it. Jewelry makers electroplate silver and gold on less expensive metals. These ornaments have the appearance of silver or gold but are much less expensive. Tin cans used for storing food are made by electroplating tin onto iron. Tin is less reactive than iron. Thus, food does not come into contact with iron and is protected from getting spoiled. Iron is used in bridges and automobiles to provide strength. However, iron tends to corrode and rust. So, a coating of zinc is deposited on iron to protect it from corrosion and formation of rust.